Hello everyone. Today we're going to look at various transformations for our functions graphs. So in geometry, we learned about 4 different kinds of transformations: translations, reflections, rotations, and dilations. In Algebra 2, we're only going to do translations, dilations, and reflections. So first we're going to investigate what is a translation. Now for this, we're going to work with this particular function throughout our lesson. We have in each type of transformation, as we go through it, we have various columns that we're going to fill out. This first column is all of the x values that are represented in my function. And then the f of x column, that's where we write down the y values. Remember that f of x in function notation represents the y. Now this one that we have on the graph, this is f of x. And what we're going to end up graphing is some type of g of x, meaning that it has some type of transformation from the function of f of x. So first let's find these y values. So when x is -3, the y value is -2. When x is -1, f of x is also -2. For f of 0, because that's function notation, right? So once again, when you have an x value and you put it in function notation, f of 0 would mean I want to know the y value when x is 0. So f of 0 is also 0. F of 1 would be 2, and f of 3 would also be 2. Now here we see f of x plus 2. This means I'm going to take all of my y values and I'm going to add 2. So if I add 2 to everything from this column, that would give me 0, 0, 2, 4, and 4. And now I'm going to go ahead and graph that. So I'm going to use these x values, because I didn't do anything to the x values, and I'm going to plot them with my new y values. So when x is -3, my y is 0. At x is -1, 0, 0, 2, 1, 4, and 3, 4. And we can see that my graph did not change shape, it did not change size, but in fact, it just moved up 2. So whenever you're adding or subtracting values to your y, that means that it's going to shift up and down. So since I added 2, my graph shifted up 2. Now I can expect that for the next column, when I take all of my original y values and I subtract 1, then my original graph here is going to shift down 1. And we're going to see that now. So I'm going to take all of these y values and I'm going to subtract 1. -2 minus 1 is -3. Then -3 again. 0 minus 1 is -1. 2 minus 1 is 1. And then 1 again. So now I'm going to graph those same x values with my new y values. So we have -3, -3, -1, -3, 0, -1, 1, 1, and 3, 1. And again, we can see that my graph was shifted down 1 from the original. So this would be f of x minus 1, and then the one that we added to would be f of x plus 2. So whatever you do to the y's is going to affect your graph vertically because y's run up and down. Now when we go to the x's, you see that here this looks different, right? The -1 and the +1 is no longer after the parentheses, but it is within the parentheses. Now I have the explanation here as to why we're going to do what we're going to do. Basically, whatever is inside of the parentheses is going to affect the x values. Okay, and whatever we do to the x's, we have to do the opposite of what it says. So here is an example. The reasoning behind this would be if we have x minus 1, which is what we're going to do here, and it's going to equal to that x value, which is -3. If we solve for x, I would have to add 1 to the opposite side, meaning we're doing the opposite. Sometimes this is kind of hard to understand. So bottom line, whatever is inside the parentheses, whatever you're going to apply to the x, we do the opposite of what the parentheses says. So instead of -1, we are going to add 1 to all of these x values. And if we do that, this column will read -2, 0, 1, 2, and 4. So now I'm going to go ahead and graph these x values with my original y values since I did not touch those y's. So at -2, we have the y value of -2. At 0, -2, 1, 0, 2, 2, and 4, 2. And we can see that this graph shifted to the right 1 unit. So normally when we see x -1, we know it's going to affect the x's, so it has to move side to side. And normally what we would think is that it would move to the left 1. But remember that you're doing the opposite. So instead of moving to the left, it's actually moving to the right. So this one here represents f of x -1. Now we're going to do f of x plus 1. So if we're following the same logic, whatever is inside of the parentheses, we have to do the opposite. So instead of adding 1, I'm going to subtract 1. So I'm going to take all of my original x values and I'm going to subtract 1 from each of them, making this column -4, -2, -1, 0, and 2. And now I'm going to graph these x values with my original y values. So we have -4, -2, -2, -2, -1, 0, 0, 2, and 2, 2. And we can see from the graph that it shifted to the left 1. So this would be f of x plus 1. Now I put this here in red because it's very important. If you have something inside the parentheses, then it is affecting your x values. So think, inside, not only is it with the x, but inside, think input. And what are my inputs? The x's. And whatever is inside the parentheses, you must do the opposite of what it says. Now, if you have something outside the parentheses, that is affecting your y values. So think, not only is it outside with f of x, which represents y's, but outside, think output. Output are your y values, and you do exactly the same as what it says. So to wrap up translations, if I look at the transformed equation, I know what my graph is going to do. Whatever is inside of the parentheses is how it's moving left or right, and we have to think of the opposite. And whatever is outside the parentheses is affecting the y values, and we would do the same. So f of x -1 minus 3 would mean that it would move to the right 1 and also down 3. For this next example, f of x minus 6 plus 7, it would move to the right 6 and up 7. For f of x plus 2 minus 4, it would move to the left 2 and then down 4. And finally, for f of x plus 8 plus 5, this would move to the left 8 and up 5. Moving on to our next transformation are dilations. Now there are technically 4 types of dilations. We have vertical stretches, vertical shrinks or compressions. Compressions and shrinks are the same thing. Horizontal stretches and horizontal shrinks. And it all depends on what number is being multiplied or divided. So notice that all of our transformations have a particular operation. So translations are when you're adding and subtracting a number. Dilations are when you're multiplying or dividing a number. So we see here in this first table, we have again our x and our y values for the original function, but we want to graph 2f of x. Now notice this number 2, this means that we're multiplying 2 to all of the y values. If you're multiplying your y values by anything, or if you're multiplying anything, whatever you're multiplying is going to grow, because when you multiply, the numbers get bigger. Therefore, we can expect that this would be a type of stretch, because if it's bigger, it's going to get longer, or larger, or taller, whatever. So I'm going to take all of these y values and I'm going to multiply them by 2. So that would make this column -4, -4, 0, 4, and 4. So I'm going to graph these original x's with my new y's. So we have -3, -4, -1, -4, 0, 0, 1, 4, and 3, 4. And we can see that my graph here got taller. This is an example of a vertical stretch because it stretched out, but vertically, since the y values are what grew. Now in this other chart here, you see that we have the number 1/2 times f of x. Multiplying by 1/2 is the same thing as dividing by 2. And when we divide numbers, those numbers are going to get smaller. So if they get smaller, we can expect our graph to shrink. So this would be an example of a vertical shrink. And we're going to see that now. So I'm going to take all of these y values and divide everything by 2. So this column would read -1, -1, 0, 1, and 1. And again, I did nothing to my x's, so I'm going to plot my same x's with these new y's. So we have -3, -1, -1, -1, 0, 0, 1, 1, and 3, 1. And we can see that it got shorter. So this is an example of a vertical shrink. Now we're going to investigate horizontal stretches and shrinks. Here you'll notice that the 1/2 is inside of the parentheses with the x. That means that it is going to affect your x values. And remember what I said earlier, whatever it says for you to do inside of the parentheses, you must do the opposite. So instead of dividing by 2, I am going to multiply the x's by 2. So all of these x's here, if I multiply them by 2, I would get -6, -2, 0, 2, and 6. And now I'm going to graph my new x's with my original y's since I did not do anything to those y's. So we have -6, -2, -2, -2, 0, 0, 2, 2, and 6, 2. And we can see that it got longer. It's like as if we stretched it, but horizontally from the sides. So kind of like an accordion. Like think of when you, like if you see an accordion, you either stretch it out or you pull it in. So this is a horizontal stretch. Now over here we have f of 2x. So even though in the parentheses it says to multiply the x's by 2, what we're really going to do to those x's are divide them by 2. -3 divided by 2 is -1.5. -1 divided by 2 is -0.5. 0 divided by anything is 0. 1 divided by 2 is 0.5. And 3 divided by 2 is 1.5. So now I'm going to go ahead and graph these new x's with my original y's. Now these here, every line is 0.5. So -1.5 is this one here, -2, -0.5, -2, 0, 0, 0.5, 2, and 1.5, 2. And again, we can see that it shrank, but horizontally. So this is an example of a horizontal shrink. So to wrap up translations, dilations. When you have a number being multiplied outside with f of x, this represents some kind of vertical stretch or compression, which remember I said is the same thing as a shrink. If a is greater than 1, so this number here, whatever we're multiplying is like 2, 3, 4, right? When you multiply a number, it will get bigger. So this is an example of a vertical stretch. Whereas if a was in between 0 and 1, meaning a fraction. Remember, fractions indicate that you will be dividing. So if you're dividing a number, it's going to get smaller. So this would be a vertical shrink. Now, if you have a number inside with the x that is either multiplied or divided, this is a horizontal stretch or compression or shrink, whatever you want to call it. If you have a whole number, remember whatever is inside of that parentheses, you actually do the opposite. So like when we had f of 2x, we actually divided. So this would be that we would be dividing by that number, and therefore this would be a shrink. If whatever is in here is a fraction, right, instead of dividing, we would actually multiply. And if we multiply, it's going to get bigger, so that would be a stretch. Our last transformation are reflections. Now reflections are negative, so only when you have negative y or negative x, okay? So negatives do not coincide with dilations. Sometimes we tend to get them confused, right? So remember I said that there's an operation for every type of transformation. Translations, adding or subtracting, dilations are multiplying or dividing, and then reflections are the negatives. So for this one in particular, we have our x values, we have our y values, we have a different graph here this time. If I applied a negative, you see how it is outside with the f of x. We are going to take all of our original y's and switch all their signs. That's what negatives do. Think about it as if you're multiplying by -1. And when you multiply or divide by a negative, it changes all of those signs. So this column would read -1, 2, -3, and 0. Now if I were to graph my original x's with my new y's, I would have -3, -1, -2, 2, 0, -3, and 1, 0. If I connect all my dots, we can see here that it reflected vertically, right? Because it is outside with the y value, so it's going to be some kind of vertical transformation. It is a vertical reflection, but the line of reflection, meaning where it's flipping over, is the x-axis. So the graph of g of x, which is equal to negative f of x, is a reflection across the x-axis. Whereas in this example, we can expect if you have a negative inside the parentheses. Now I know I said that whatever is inside the parentheses, you're going to do the opposite. Well, the opposite of multiplying a -1 would be to divide a -1, which would still give you a negative number. So regardless of whether you have a negative inside with the x, you are going to still apply that negative, meaning change all of your signs. So this -3 would become a +3, the -2 become a +2, 0 is just 0, and 1 would become a -1. So these are my new x's, and I'm going to graph it with my original y's, and we're going to see what happens. So we have 3, 1, oops, over here. Then 2, -2, 0, 3, and finally -1, 0. And if I connect those dots, we can see that it flipped, right? It reflected, but horizontally. And when it reflects horizontally, because remember, it did affect your x's, so it's going to be a horizontal transformation, it is flipping over the y-axis. So therefore, the graph of g of x, which is equal to f of -x, is a reflection across the y-axis. Now you're going to see in future problems when we do reflections, sometimes our reflections show us that we end up with the same exact graph. And this is because graphs can have symmetry. Now there are 3 types of symmetry. We have x-axis symmetry, y-axis symmetry, and origin symmetry. With x and y-axis symmetry, it is a line that can cut our graph in half. Okay, this is called line symmetry. That line of reflection will cut your graph. So When we have x-axis symmetry, okay, if I were to draw a vertical line through it, we see that we cross 2 points, meaning that here at x is equal to 2, we end up with 2 different y values, and these x's repeat. Therefore, this is not a function, which we are only focused on functions, so we are not going to see graphs that have x-axis symmetry. However, when we have y-axis symmetry, which can happen, all right? It means that if I reflect this graph over the y-axis, it would look exactly the same. Okay, this is called an even function. Now, it's called an even function because functions that have this kind of symmetry typically have exponents that are all even. Don't worry, you're not really going to see that quite yet, but that's why it's called an even function. Now, origin symmetry is a little different. Origin symmetry is not line symmetry, it is rotational symmetry, meaning if I were to turn this upside down, it looks exactly the same as my original function. See? This is called odd functions. Now, an odd function is called that because these kinds of functions typically have exponents that are all odd. Okay, so that's the reasoning why they're called even and odd. For right now, all I want you to be able to do is be able to identify if you're looking at an even function or an odd function. So let's look at some examples. So what we look for each one of these is we check their symmetry. Where is it symmetric? If it has rotational symmetry, meaning I can turn it upside down, it is an odd function. If it has line symmetry along the y-axis, that means it is an even function. So for example, this one here, I notice if I were to flip it upside down, it looks the same as my original. So this is considered an odd function. This one is the same situation. If I were to turn this upside down, it would look identical, also making it odd. Here, I can tell that if I were to draw this line right down the middle, the left side is identical to the right side, meaning this is an even function because it is symmetric along the y-axis. Now this one up here, if I draw a line across the y-axis, the left is not the same as the right. If I turn it upside down, it does not look the same as my original. Therefore, this is neither. Not all functions have symmetry. And if they don't, that's okay. So this one is neither even nor odd. This one is another example of an even function. It is symmetric along the y-axis. So this is even. And those are our transformations.